Hello, everybody. Welcome to the MIT Category Seminar. Today, we're going to talk about entropy. Much looking forward to that. So we have Carmen Constantin. Hello, Carmen.
Hello.
When you're ready.
Okay, well, thanks for inviting me, Paolo. I'm really happy that there are so many online events these days. It's much easier to participate than in person. So this is a talk on a project which I did a while ago, but it was good to it was good for me to refresh my memory a bit, also because there are some new directions which I'm hoping to develop from it now, and we'll talk about those later. So the talk is about entropy, how to define entropy in a category theoretic way using pre-sheaves, and what are the advantages that you gain by using this more general topos of pre-sheaves. So the outline of the talk is we'll start with a bit of mathematical vocabulary, actually quite a bit of mathematical vocabulary until we get to define entropy. Hopefully it won't be too dry. It's illustrated with a lot of physical references, so it should be like an illustrated algebraic geometry book. Then we'll go to the contextual entropy construction and we'll define that and see what properties it has. And perhaps its most surprising property is that it's rich enough to encode full information about quantum state. So it's a state invariant. And then I'll just summarize what we said and give some new perspectives. Okay, so the background is that we're mostly working in pre-sheaf toposes over some physically meaningful base category. So if you want a gentle introduction to toposes, then I'd recommend this book called 7 Sketches. In the last chapter, there's a very nice introduction to toposes in terms of behavioral systems. Toposes is a way to capture behavior. And there, the perspective is that toposes capture things that evolve over time. So the base category is basically time. Here, the base category is also meaningful, but not in the sense of time evolution, rather in the sense of contextuality. You look at the quantum system through many classical snapshots, and the classical snapshots are encoded in this base category. So pre-sheaf, in case you're not familiar with the term, is just a functor. It's a functor from some kind of category, actually from the opposite of some kind of category into the category of sets. And that's why we see it as a generalized set. It's basically not just one set, but a family of sets, one for every object of the category C, but not just any odd collection of sets, but a collection of sets that that you keep track of their interactions as well. So the objects in C are related to each other. If you think of a very simple category, just like we will have here, namely a poset, then you will have some maps which tell you that one element of a poset sits below a different element of the poset. And then when some element of the poset sits below a different one, it means it's smaller in some sense. You can think of it as a smaller perspective or a smaller object. And so you should have a restriction map. And that's why the pre-sheaf is a contravariant functor, because the restriction map does not restrict from the smaller set to the larger set, but obviously from the larger set, it should make sense to restrict to the smaller set. So there's restriction maps go in the different way to the arrows of the base category C. And in the limit case, when you take a very trivial base category, just a terminal category, which has only one object, T, and one arrow, the identity arrow on that object, a pre-sheaf over the terminal category is just a set, which is philosophically quite a nice way of saying that classical mechanics can arise as a limit of quantum mechanics, the limit being over the set of categories. Once you reduce your base category to the trivial one, then what you should get is classical. And the idea is that we're going to articulate a lot of fundamental physical concepts in terms of sets and functions. And this is what the next few slides will be about. So first of all, we're going to look at this classical versus quantum picture. Actually, the picture is only really in the classical case. If you think of classical physics in the most fundamental way, it's represented by a state space, which is just some sort of set of states. Usually, it has a bit more structure than being just a set, but in its most basic case, you can say it's just a collection of points, the points being the states. So the pure states are just points which belong to the state space. And then mixed states are probability measures, which assign some value between 0 and 1 to all the subsets of the state space. In such a way, of course, that the whole space is assigned the value 1. And of course, you would want it to be additive with respect to unions in a suitable sense, which we're going to see into more detail later. Then you don't want just some state space, you also want to observe things that, observables that, you want to measure observables that are related to the states your system can be in. And the results of those measurements usually live in R, the real numbers. So observables are just functions from the state space to R, which associate to every state some particular real value. And you also have a nice way to talk about propositions by going in the other way. So you can say, maybe your function f represents energy, and maybe your question is, the energy of the system is between 0 and 5, or lies in some interval delta. And if your proposition is of that form, the system has energy within the interval delta, then the proposition is actually the inverse image of that interval delta, which is just a subset of S. It's an element of the power set. So F minus 1 of delta being a subset represents a proposition. And then you can form a whole logic with these propositions, which is Boolean. So subsets correspond to propositions, conjunction corresponds to intersection, and disjunction corresponds to union, and negation corresponds to complement, and so on. So also you can define a notion of entropy, and the entropy in classical mechanics is the Shannon entropy, which takes a probability distribution, usually on the set of states, and send it to a real value. Okay, so there's a quantum picture as well, although you can't make a nice drawing as in the classical case. But in quantum mechanics, you usually describe the system state space by a Hilbert space. And you also have a notion of pure states. Now, they are not just elements of the Hilbert space, they are vectors, unit vectors that live in Hilbert space. So the collection of all rays gives you the collection of all states. Mixed states are then density matrices, or you can think of them as bounded operators that live in Hilbert space. Values are also real numbers. Observables are self-adjoint operators in Hilbert space. Propositions are projections. That means p square equals p. So they're self-adjoint operators, but also projections. And there is some sort of logic which is given by the propositions, only this logic is not necessarily distributive. So the joke being that if you are at the quantum hotel and you order eggs or ham and bacon, what you get is not necessarily eggs or ham, eggs and ham or bacon. You don't necessarily get eggs and ham or eggs and bacon. So it's not a distributive logic. And there is a notion of entropy as well, which is defined on the set of density matrices with values in R. And our motivation for the topos approach, or one of the many motivations for the topos approach, is that the quantum picture doesn't really have a nice geometrical interpretation. So classically, there is a duality between the state space and the observables, because the collection of observables, the collection of functions, form a commutative C-star algebra, because you can add them pointwise. So you can do things like f of s plus f plus g of s. We can hold this to be f plus g of s. So under these pointwise operations, you get the commutative C-star algebra. And there is a nice result called Gelfand duality, which gives equivalence of categories between unital commutative C-star algebras and compact Hausdorff spaces. So in one way, the duality takes a C-star algebra A and gives the spectrum of A, that is the set of all pure states on A, which means the set of all functions defined on that algebra with values in R such that f is positive, linear, multiplicative, and moreover norm 1. And this can be shown to have a topological structure under the weak star topology, which makes it a compact Hausdorff space. You can also go in the other direction. You can take a compact Hausdorff space X and look at the collection of all continuous maps on it. And that is a commutative C-star algebra, as we have seen in the previous slide on the pointwise operations. And now in the quantum case, quantum systems have non-commutative algebras of observables. So you can't use this duality to obtain a geometric picture. So in the topos of sets and functions, if you insist to live in that topos, which has these fairly trivial pre-sheaves over the terminal base category, classical and quantum mechanics appear structurally different, at least from this geometric point of view, and also in terms of many no-go theorems, most of them related to contextuality. So the idea is to move away from this trivial base category by taking classical snapshots of a quantum system. So given a quantum system, you look for a base category where the objects will correspond to all possible classical perspectives, all the windows on the system through which the system, the truncated version of the system that you see, looks classical and behaves classically. And the morphisms will indicate how these perspectives relate to each other. So in particular, some windows will be larger than others and you'll be able to see more through them. And then the idea is to construct a pre-sheaf over this base category by attaching a classical state space to every object in the base category, which you can do using classical results such as Gelfand duality. And the pre-sheaf will then play the role of state space in a way that's structurally analogous to the classical situation. So just a sneak preview of how familiar concepts should look like in this new topos. The state space, which used to be a set, is now this spectral pre-sheaf, which is no longer a set, but a generalized set, so a varying set. It's a pre-sheaf which is defined on some category of contexts with values in sets. So a collection of sets for every classical context. Pure states used to be points. A very deep result in the topos approach is that the spectral pre-sheaf doesn't have points. And this actually is equivalent to the Cohen-Specker theorem, that the absence of points of the spectral pre-sheaf. And it was one of the, this very nice formulation of the Cohen-Speckler theorem in terms of the absence of points of the spectral pre-sheaf is one of the very nice results that laid at the foundation of this topos approach. I should say also that before moving on, that these pseudo points are measures which are minimal in a certain sense. So just like mixed states used to be measures on S, oh, I made a typo, which will probably carry on everywhere, but it's power set of S in zero. Measures from power set of S to zero, sigma. So now we're not looking at the power set of sigma, we are looking at all the sub-objects of sigma, in particular the clopen ones, the ones which are both closed and open. And amongst these measures, some of them will be minimal. It's not relevant for us here necessarily, but those are the points, the pseudo points. Values are more general now in this new language. So they are no longer just a set R of real numbers, but they are pre-sheaves of real numbers. And moreover, these pre-sheaves will associate a number to each context, but then they will also have to associate a restriction map between these values. And whether these are going to be order preserving or order reversing restriction maps is indicated by this less than or equal to or greater than equal to symbol. And then you can also use various sub pre-sheaves of these two basic pre-sheaves. And a nice thing is that observables, if you do some magic with, if you look at spectra decompositions, the observables turn out to be maps from the state space to the real numbers, just like in the classical case where observables were functions. Now, of course, these are pre-sheaves, so they are not functions, they are natural transformations between sigma and the real number object. Propositions used to be projections, but now we can take every projection and turn it into a sub-object of the quantum state space sigma, the spectral pre-sheaf, in a way that's analogous to the way that propositions used to be subsets of the state space. But then, of course, there are more sub-objects of the spectral pre-sheaf than those that come from Daseinization of projections. So that gives a richer logic, which is distributive. It's the logic that comes associated with every topos. So every topos has its own internal logic, which is intuitionistic. And the point of this talk is to complete the last row of this table and show how you can define entropy in this more general language. What will it be? And just like it used to be a map between probability distributions and R, now it's a map between measures on the spectral pre-sheaf, denoted by this curly M, to global sections of the real number object. For global sections, you can think of them as category theoretic points. They are points from the trivial pre-sheaf, the terminal one, over that base category to R. So actually a choice of a point at every set of the pre-sheaf.
Sorry, Carmen, there is a question.
Yes.
Can you go back one slide?
Yes.
So David's asking, which sort of restriction maps does R to the less or equal, I guess on the fourth line, have? When you restrict, does the number increase or decrease?
So yeah, it's hard to remember for me as well, but I remember it by saying that, well, if you have the numbers on the real line, then they should increase. So if it's this symbol here, it means these are order preserving. Order preserving maps. And if it's this thing here, then this is order reversing. And in particular, I'll have a slide just dedicated to these objects, but in particular, the global sections, they will turn out to be order preserving maps from the base category to R. So hopefully this will become clearer. But that's how I remember the less than or equal, greater than or equal symbols. So these guys are order preserving.
Thank you. There's another question actually.
Okay, go on.
Things goes asking, does QM star generalize QM in any way, or is it a very new way to quantize?
Does QM star generalize QM? QM star is I should have called it the TA or something for a topos approach. So this is part of a wider program. So kind of what I brought to this program is this part over here. Everything above was developed by Chris Isham and Jeremy Butterfield and Andreas Döring to a large extent. And Cecilia Flori worked on this as well. So it's a different approach to quantum mechanics, one that's structurally different. So it's trying to bypass some of the conceptual issues, I think, the non-realism of quantum mechanics, for example, the fact that in quantum mechanics, observables don't have values unless you measure them. So states do not have values. You cannot assign a value to every quantity unless you measure it, which is, well, philosophically displeasing, I suppose. Reality should have a value. So, of course, there are very strong no-go theorems which guarantee that you cannot assign values to all states independent of their context. And these are contextuality theorems, such as Cohen-Specker. But what we have here is a way to bypass this by just lifting our discourse to a higher level of generality. So in the topos of states, no, you cannot assign values. If the values are just real numbers, you cannot assign a real number to every state. But if you work in a more general topos and your values are these generalized real number objects, then suddenly you can assign values to every observable. So the observables suddenly become maps from sigma to the real number object. And it's perfectly possible to assign values, but the catch is that sigma hasn't got points. If sigma would have had a point, then that point would have given you a way to assign value to every state independent of its context. So you can read more. I think a classical, albeit lengthy reference is called "What is a Thing?" It starts with a very nice philosophical introduction as well. So I can write it here.
Yes, please.
What is a thing? By Chris Isham and Andreas Döring. And then I think if you sort of chase the references, there's quite a few which talk about, I think this is maybe the nicest aesthetically, apart from the entropy, of course, which I'm personally very attached to. But the deal with the observables, which suddenly have values, I found particularly pleasing. I should also say, in case anyone thinks that I'm very experienced in physics, I'm not. I never really understood physics as a high school student. I did maths as an undergraduate, and when I stumbled across this explanation of quantum mechanics, I thought, oh, this is beautiful. It finally makes sense. I mean, it's just a set, and the C-star algebra on that set, and its Gelfand dual is the state space. I mean, why didn't they teach it like this in high school? It was, I felt very, very at home in this approach. I found it at least aesthetically very, very nice. So, are there any more questions before I move on?
Yeah, there's one more. So Henrik is asking, and the logic now, I guess in QM star has become associative, I guess distributive, that means?
What's that?
But is asking if the logic now has become associative, where I think they mean distributive.
A distributive, probably they mean. Associative, it used to be before as well. Yes, the logic is distributive. So if you determine, because you, for the logic, you choose the collection of Clopen subobjects of sigma. And these subobjects are not all coming from projections. Of course, the parts which come from projections behave just as you would expect them to, and they're not necessarily distributive, but because you have extra ones, this fixes the problem. And if you want to read about the logic more, I also, again, recommend going to this 7 Sketches book. It has to be the nicest, simplest introduction to logic that I've yet come across in general toposes. So the logic is usually defined, I'm not going to go into very many details here, but it's usually defined in terms of something called a subobject classifier. So subobject classifier tells you if an element is a member of a set or not in sets. So that's why you have characteristic functions, which assign 0 and 1. So you have 0 if it's a member of a set and 1 if it's not. And now you have kind of the same, but instead of a function which assigns 0 and 1, you have a natural transformation which assigns 0 and 1 in every set in such a way that if you've chosen something at some point, you have to choose it under restriction maps. So it's not just all possible combinations. It's just the ones which agree under restriction maps. And then you can use the Yoneda embedding to show that this gives you just a set of sieves for the truth value. So the logic is no longer Boolean. That's also perhaps worth mentioning, because we're used to thinking in Boolean terms because we live in a macroscopic universe where things are either here or they're not. So in quantum mechanics, things are in a superposition of states and they're not necessarily either here or not here. So it's, perhaps if we lived in a quantum world, if we're more aware of the fact that we're living in a quantum world, we wouldn't find it so surprising that the logic is not necessarily two-valued. So, and also I find it intriguing that this topos theory revolution, which kind of changed the axioms of mathematics, this category theory revolution of the foundations of mathematics happened roughly at the same time as the quantum change of perspective, which revolutionized the way that we understand the real world. So it's I don't know enough the historical development to know if these are related, but at least it's an interesting coincidence. It's almost as if your experience, your direct experience of the real world shapes the language that you use to describe it in some way. Almost as if mathematicians and physicists were talking to each other. So, okay, the base category. Let N be the non-commutative algebra associated with a quantum system. So that means, in case you're wondering what could an example of a nice non-commutative algebra be, just take a Hilbert space and take the algebra of all operators on Hilbert space. So think of matrices as a very down-to-earth example. Think of matrices. Matrices are not commutative. So choose as the base category the poset of commutative subalgebras ordered by inclusion. And a result that we'll be using throughout the talk is that every commutative subalgebra is generated by a collection of projections. It's generated by a set of projections via the double commutant construction, where one commutant, if you take the commutant of a set, it means you take all the elements of N, which commute with the elements, so this is some set X, then X star, X prime is all the S in N, such that SP equals PS, so P in X. Okay, and the double commutant is you take this new set and you do the commutant again. But basically what's what's important and essential to remember about this is that this choice of projections which generate an algebra via double Newton construction is canonical. So it's almost like a base. And in a sense, it is a base because these projections give you the set of eigenstates, of common eigenstates of the operators that live in the algebra V. So every operator that lives in the algebra V has a spectral decomposition. And the spectral decomposition in terms of a sum of eigenvalues times eigenvectors, so eigenvalues times projections, tells you what possible values can you have upon measurement. So upon measuring an operator, you will get one of the eigenvalues, and the system will collapse to the eigenstate corresponding to that eigenvalue. And,
sorry?
Yes?
Can I make a question? So there is no like hypothesis here of like finiteness. I mean, like this is valid completely in general, or you need some like technical?
No, this is valid. This is
because you're talking about like the spectral decompositions as eigenvectors and eigenvalues, but like in general, I mean, if you consider just any self-adjoint operator, like the spectral decomposition would look like more complicated. No?
I guess what I was meaning to say by the spectral decomposition is that the observables which commute have a joint collection of eigenvectors. And those eigenvectors are given by these projections. So these projections, they correspond to the subspaces, which are the eigenstates of those self-adjoint operators which commute with each other in this context.
Okay, so this common eigenspace is always finite dimensional.
Well, we are in finite dimensions. Yes, I should say that this works in finite dimensions. So everything that's happening here is happening in finite dimensions. Although okay. I think there is a way to extend this to the infinite dimensional case, which I didn't have time to look at when I was doing this project, but it would be an interesting thing to explore because most of the results that this project, the further work sort of hinges upon, work in infinite dimensions as well.
Okay, that was my question. Yeah, of course, that must be like technically a bit more complicated, but probably in principle it's not that different. Thanks.
Yeah, I mean, it's yeah, that's the idea. And then the connection with projective measurements is that there's a nice connection with measurement is that these PIs, they sum to the identity. So they form a resolution of the identity, and that's what the projective measurement is. It tells you that, well, you have some probabilities of obtaining each eigenvalue, which are given by some sort of traces that you compute with these operators. We'll see them in a second. And now, if you take some subalgebra, so if you take some smaller window, then the smaller window is generated by partitioning the set of PIs and summing the elements in every partition class. So you can think of this as saying, okay, every P here gives me its corresponding eigenvalue, gives me a possible outcome of measurement. But I could say, I don't want to know so many possible outcomes. I want to say, join the first two together. I don't want to distinguish between the first outcome and the second outcome. They'll be the same as far as I'm concerned, and all the others I keep distinct. Right? Then I've got a coarse graining that's going on. So this coarse graining is done by summing the projections which I don't want to distinguish their corresponding outcomes. And once I've summed them and I've done the double commuting construction of those, I will get a subalgebra, which will also have a number of self-adjoint operators which commute with each other. And moreover, they will be a subset of the set of self-adjoint operators which commute with each other in V. So for example, I could take this V prime, which is P1, P2, P3. So I don't distinguish between the first three and I leave the others intact. And that's going to be included in V. And just a note, you can have maximal subalgebras. so maximal windows, which are given by rank 1 projections. So they're the finest resolutions of the identity that you can possibly find, are given by orthonormal bases of Hilbert space. And each orthonormal basis, you can turn, each vector of an orthonormal basis, you can turn into a projection. These are going to be orthogonal because they're a basis, and they're going to sum up to the identity. So this is the generating set of a maximal algebra. And then you can have minimal algebras where you just choose one projection and you choose the identity minus that projection. So that's two-dimensional algebra. And we'll use both in the both types of algebras in the coming discussion. Okay, so finally we can construct the state space object. We've got just about the right ingredients. And it's a pre-sheaf. It's defined on the set of contexts, op, which is a poset. So as a poset, it's a category with values in set. How do we define that? Well, to every object V, to every context, you associate the spectrum on V, which, if you may remember from a few slides ago, it's the set of functionals on V, so the set of functions from V to R, which had some properties. They were linear, multiplicative, norm 1, and what? And positive. And on arrows, you have restriction maps going from such a set of functions from V to R. If V prime is a smaller algebra, you just restrict each map to V prime. And if you wonder what these functions do in practice, actually, because they're linear and multiplicative, it means that it's enough to define the function on the generating set of projections. Once you've defined them on the generating set of projections, every other operator in V, you can get as almost as a basis. You can get by linearly adding and multiplying the projection. So also because they're multiplicative, on the set of projections that generates V, you can only associate 0 and 1 because f of p squared is equal to f of p squared and is equal to f of p. So it has to be only 0 and 1 because it's positive. So basically what you're doing is you're taking every generating projection in V and you're assigning it 0 and 1 in such a way that they all sum up to 1. So you're only allowed to assign 1, 1 basically. And then when you do the restriction, you have to assign something to the new set of projections, which is now done by joining together bunches of projections from V. How do you do that? Well, you just add whatever F assigns those projections, and that will give you a new assignment on the projections of V prime, which will still satisfy this requirement that they add up to 1, because the total sum is 1 in both cases. Okay, so now that we have a state space object, we are also interested in its subsets. And subsets are sub-pre-sheaves. And sub-pre-sheaves mean pre-sheaves which at every object give a subset of the state space. And these form a lattice. So for every 2 sub-pre-sheaves, every 2 stage-wise subsets you can think of, S1 and S2, you can define their meet and their join. And you define them in every context. For S1 join S2, for example, at the context V is just S1 at V join S2 of V. And there's an important part of, an important class of sub-objects are the Clopen ones. Those are the sub-pre-sheaves such that every component at every V is a Clopen subset of sigma V at all contexts. And these, the Clopen subobjects, correspond to the Borel sets, to the measurable subsets of state space that we used in classical mechanics. They are the quantum analog. And they form Heyting algebra under this stage-wise meet and join operation.
Sorry, could you say another word or like about these topological spaces sigma b? I mean, more, is there an easy picture like of how they look like, or what is a Klopen subset of such a space?
An easy picture. Well, I can't draw that easy a picture. I've got a sort of easy algebraic description in my thesis, which you could look up. But what they look up is basically, if you remember these potato pictures, you used to have a potato picture over the trivial base, whereas now you have more. And then if two sets are included in each other, then there's restriction maps going from these potato pictures. Basically, that's kind of what it looks like. It looks like a bunch of potato pictures. And then does this poset look like? That's the only question, really. What does the poset look like? Well, it has a bunch of maximal subalgebras. And then the maximal subalgebras all have these are dimension n, 2 level, and so on, until you get all the way down to dimension.
Yeah. Yeah, that's a picture of a pre-sheaf, let's say. But like my question was more specific to this like topological spaces that you build as a spec of V, and like because you anyway these Klopen subsets of this sigma V play a very important role now, because it's what you are defining as, I don't know, I guess that these are your pseudo points later, no? So that, yeah, that was my question concerned this Klopen subsets, if you want, very well, doesn't matter.
Okay, well, I don't have a sort of easy answer to that, shall we say. I mean, there's a lot of algebra to define sigma at every V, but maybe it's not going to be that useful for the coming talk. What is important to know is that is the structure that these Klopen subsets, this lattice structure, which lives on the Klopen subsets. So at every V, you have a lattice isomorphism between the set of projections in V and the Klopen subsets of sigma V. So sigma V here this is just a set. So this is the analogy between the projections, which used to give you the logic, and the subsets. The subsets give you the logic in classical mechanics. And this lattice isomorphism basically takes a projection and it maps it to that subset, which consists of those functionals, so those maps from sigma V, from V to R, which assign 1 to the projection P. You remember I told you that the projections can only be assigned the value 0 or 1. And only one of them, one of the ones in the generating set, can be assigned 1. Of course, there are more projections, not just the ones in the generating set. But from the generating set, only 1 can be assigned the value 1. And those states, these Fs, these are called states. So those states which assign the value 1 to P, they are the ones which live in the in this SP of V. Okay. So given some global proposition, whole algebra, you can approximate it in every context. So you can approximate it from above, or you can approximate from below. And here we approach those projections which live in V and are above P. Of course, you could approximate it from below by taking the join of all those projections which are less than P. And if P happens to live in the context V, then this approximation gives you just P, trivially. So this is almost like you're making a sentence about a quantum object, but you have to restrict your sentence to restrict it. You approximate it as best you can.
Sorry, Carmen, there was a glitch in the connection. Could you please repeat the last sentence?
So there's this is a way of approximating a sentence that you make, proposition that you make about a quantum state to a quantum object to the classical context that you have access to. So you're restricting your attention to the classical object and you're reinterpreting your proposition. You're giving an approximation that makes sense in that context. So this approximation then corresponds to a Klopen subset of sigma v. And the nicest thing is that you can glue together these Klopen subsets. You can take their collection and together with the restriction maps, they form a sub-object of sigma. And this sub-object is called the Daseinization of P, because suddenly from one projection, you've got a collection of sub-objects, one at every V. Okay, so finally, the last ingredient, I think, last but one ingredient is constructing number objects. So this real number pre-sheaf, which lives over the same base categories of context, is defined on objects to be the set of order-preserving functions from the downset of V, at every V. The downset of V meaning all those contexts which are included in V, with values in R. And then on arrows, you have the restriction map that goes from such a function to the function restricted to the downset of V prime, if V prime is some smaller context. And our global section corresponds to an order preserving function from the poset CFN to R seen as poset. And you can see why that happens, because basically you're choosing something for all the maximal ones, and then you have to choose smaller things for all the smaller ones. And then there's an analogous pre-sheaf, which is R with the order reversing sign, and it's defined exactly the same on downsets, only the functions are order reversing, and the global sections are order reversing functions from the poset to R. And then to define the measures, you're going to use a sub pre-sheaf of this order reversing pre-sheaf, because you're not going to need all of R, you're just going to need 0, 1. So in this definition, basically just replace this with 0, 1. That's all that's needed. So a measure becomes a map between the Klopen sub-objects of sigma to the global sections of this reversing real number pre-sheaf. And it takes a sub-object S to this mu of S, where mu of S, like we've said before, because it's a global section, is actually a function from the set of contexts 2, 0, 1. That is order reversing. And what is that function in particular? It takes a context and it associates some number to it, which depends both on the context and on the sub-object that we are considering. And the measures can be defined completely abstractly. You don't need to reference the Hilbert. They satisfy these two conditions that are intuitively necessary, that the whole pre-sheaf, which is trivially a sub-object of itself, is assigned 1. So it's assigned the maximal value at every context. So the constant function 1, which assigns to every V the value 1. And moreover, if you take the measure of the join of two sub-objects and you add it to the measure of the meet of two sub-objects, just get the sum of the measures of each sub-object. And this is defined, this sum, of course, these are functions, so it's defined stage-wise at every V. And it can be shown that this measure mu induces a finitely additive probability measure on the set of projections, which by Gleason's theorem can be uniquely extended to a state of n. And there's a star. Where did I put the star here? Because this only holds if m hasn't got any I2 summons. So with apart from, for example, 2 by 2 matrices, you're thinking you're going to have some ambiguity. Otherwise, mu induces a finite additive probability measure, which becomes a state. So, and this, by state, I mean a density matrix. Think of a density matrix. So now that we've got these measures, we can define contextual probability distributions, and we're getting close to our definition of a contextual entropy, because the measure mu induces a measure m on the projections, which assigns to each projection a number in 0, 1. Namely, to the projection, it assigns whatever mu assigned to the designization of that projection at V. And the answer is yes, but it will take 3 pages to prove. So we're going to skip that. It's well defined and it's finitely additive moreover. So this is the measure that you need for using Gleason's theorem. And you can prove both. So m of 1 is 1. M of p plus q is equal to m of p plus m of q for any p and q which are orthogonal projections. Okay, and locally, so this is a global measure on the set of all projections, but of course you can restrict it to every context V. So if you restrict it to V, you get a map from the projections of V to 0, 1, and this gives you a probability distribution on that canonical generating set of V. The probability distribution is given by m restricted V of each pi, which if you add them together, because it's finitely additive and these pi's are pairwise orthogonal, it's just m restricted to V of the sum. And you might remember that the projections in the generating set added up to the identity form the resolution of the identity, so just m of the identity, which is 1. So because we have these canonical probability distributions at every context, we can associate to them a classical Shannon entropy. So we associate to every context an entropy, the number, which is given by the Shannon entropy of this probability distribution, the sum of minus pi log of pi. These are the projections. These are the probabilities, little pi, assigned to each projection, big pi. Crucially important for us is that if we have a larger context W, so a context which has more projections that can be grouped together, the entropy assigns to W something larger than it assigns to V. This is the recursion property of Shannon entropy. It's a formula plus some positive quantity. So that means that we can assemble all of these values into a map context, which is order preserving now. So E gives a map from the measures on sigma to the global sections of this order preserving real number object. And now we haven't referenced the Hilbert space formalism very much, but we should, just to see how it relates to everything we've done here. So every state, so every function from V to R, which is positive and norm 1, corresponds to some measure, mu rho. How do you define the measure? Well, it associates to every S at V whatever rho assigns to the projection corresponding to SV, where this is the inverse of that map. Remember, we had a map that was an isomorphism, a lattice isomorphism between the projections and the open subsets. This is the inverse of that map. You're taking the projection corresponding to SV. And if you're thinking of matrices, this is just the trace of rho, the density matrix, times P, the projection. And it happens to be, this is the value that M, the probability distribution on projections, assigns to in V to that projection, SV. So the von Neumann entropy of a state, rho, is defined as minus sum of lambda I log lambda I, where these are the eigenvalues of rho. Okay, and the contextual entropy encodes this as a distinguished minimum. And we're going to see why in a second. So how do we find the von Neumann entropy? Because one of the mottos of the topos approach was that you're keeping track locally of all the classical information, and that allows you to retrieve the quantum picture by taking everything into account. So how do you find, given all these Shannon entropies, yes? How do you find the quantum, the von Neumann entropy? And you can do that noting that every density matrix is diagonal with respect to some orthonormal basis of Hilbert space. And that orthonormal basis, which diagonalizes your density matrix, gives you a set of pairwise orthogonal projections which form a resolution of the identity and therefore generate some maximal context. And we call this context V rho because it's the one where in that context rho is diagonal. And then the entropy, the contextual entropy, associates to the measure corresponding to rho at this particular context V rho, the Shannon entropy of the eigenvalues of rho. Why? Because these are the small measures at V rho of each of the PIs, which means just the trace of rho times PI, which means because rho is diagonal in this basis, psi I means just rho, trace of rho PI is equal to the eigenvalue lambda I. In any, and that's the von Neumann entropy by definition. In every other basis, which is not in every other context, which is not equal to V rho, what you're going to get here is the di instead of lambda I, which will be the diagonal entry of rho in some basis in which it's not diagonal. And the Schorhorn lemma guarantees that this is minimal, this value is minimal among maximal contexts, because it guarantees that in any context where rho is not diagonal, its trace, so its diagonal entries will majorize the eigenvalues vector, and Shannon entropy is sure convex, I think, convex or concave, whichever way it is. It guarantees that amongst maximal contexts you have the minimal value where rho is diagonal. And to find this value in practice, basically you need to find the minimum of what's essentially a real value map on the set of unitaries, because all these maximal contexts can be permuted to each other. You can by a unitary matrix. So every resolution of the identity, you can think of it as corresponding to some orthonormal basis, and every unitary rotates this orthonormal basis into some other orthonormal basis. And that gives you all the possible orthonormal bases. So every unitary corresponds to some particular Shannon entropy. So finding the minimal one just corresponds to finding the minimal of a continuous real valued function on the set of unitaries. And there happen to be very nice algorithms that find this with reasonably decent speed. So some properties, just like Shannon entropy, contextual entropy is also positive, where greater than equal, I mean, these are not numbers, these are functions. So what I mean is that the function at every value v is greater than 0. But this is the 0 function. Concavity is defined also at every v. So these are functions. Remember, they're functions on Cn. So at every v, this is concave, just like Shannon entropy is. Additivity holds, meaning that if you have two states, rho 1 and rho 2, and you take their tensor, rho 1 tensor rho 2, well, I wouldn't say it holds, but I would say we define it like this. Because you wonder, why is this a definition? Because this is a function on C of n. And this is a function on C of m. because row 1 and row 2 live in different Hilbert spaces. So how do you add two functions with different domains? Well, you can't necessarily add them. So we just define their sum to be the entropy corresponding to this measure, tensor measure. And we evaluate it at the context V tensor W. And then subadditivity, which holds for von Neumann entropy and for Shannon entropy, here only holds at split context. So this greater or equal to relation holds only if you're considering contexts which are split. And I can't resist but mention that this gives a nice proof of the subadditivity of von Neumann entropy, which usually would use Klein's inequality and it would be moderately lengthy. This gives a one-line proof. So the proof says that it goes like this. You have the von Neumann entropy as some state row 1, von Neumann entropy as some state row 2. If you choose contexts V and W, where each of these states are diagonal, this is the contextual entropy at those contexts, the sum of the contextual entropy at those contexts. Then just by the additivity definition, this is the entropy of mu at row 1 tensor row 2 at V tensor W. And then by the subadditivity property, which we know holds for split contexts, this is greater than E of mu rho, where rho is some state whose partial traces are equal to row 1 and row 2. So it's greater than equal to the entropy of mu rho at V tensor W. And because of the Schur-Horn lemma, which I mentioned, this is a greater value than the von Neumann entropy of rho, which is found at that context where rho is diagonal, which is not necessarily V tensor W, it could be some other context. So you've got the subadditivity of von Neumann entropy done in one line. Just because you're working in a more general topos and things just become trivially trivial. Things which are trivial become trivially trivial. Contextual entropy is also continuous if you take a suitable metric on unitarily equivalent contexts, which means that, intuitively speaking, that if you have a basis and you don't rotate it much, then the entropy doesn't change much either. Okay, so like I promised at the beginning, this entropy construction is rich enough that it allows you to reconstruct quantum states. And this is the punchline of the talk. Because the entropy gives different values, unitarily equivalent values for different pure states, you don't lose any information with contextual entropy. With von Neumann entropy, for example, you couldn't distinguish between different pure states because they all had entropy 0. Now you have different but unitarily equivalent values. So how do you find some state psi, whose entropy equals some global section of R, some function gamma? Well, first of all, you have to find that context V where gamma gives you 0. So you have to find the minimal one. And then you have to choose some unitaries which fix exactly one of these projections. So they choose some PI and they fix it, but then they permute the others. They not permute, they don't permute the others. They change the others without permuting them. So every, if you apply that unitary to PK, it does not land in that set anymore. And once you've done this, you look at all the contexts. Imagine in 3 dimensions, you fixed one axis and you've rotated the other 2. And if you've done that for every one of your axes, there is only one context from these partially rotated contexts where the entropy will be 0. And it's the one whose projection corresponds to your state. Psi is equal to, it means that psi equals pi if the function is 0 at vi. Okay, So pure states are easy enough. Reconstructing mixed states is also not much harder. So first of all, you have to find the minimum that starts in the same way. You find some context V, where the map takes its minimal value amongst all maximal contexts. And you know that the state rho is equal to sum of lambda I pi, where pi are the generating projections. And now your task is to find these lambda i's, find the values. How do you do that? You look at all the two-dimensional contexts which belong to V. So all of these guys are included in V, and they're two-dimensional. And how do you take them? You choose some projection pi and you take its complement, I minus pi. And that generates some small context Vi. And you know that the function restricted to Vi is just the Shannon entropy of lambda I times 1 minus lambda I, whatever those values might be. But that gives you two possible values for lambda I, because imagine that this was gamma restricted to Vi was some value. Then the possible things that would generate that would be two values, x1 and x2, which are symmetric around 1/2. Just from this graph, you can read them off. So you can solve this equation and find the two possible values. And one of them will be x1 and the other one will be x2. And the question is lambda 1 equal to x1, where I assume this is the smaller one, or is it equal to x2, which is the larger one? And you have to decide which one of these lambda is equal to. And now it helps to remember that the eigenvalues have to sum to 1. And knowing that the eigenvalues have to sum to 1, you're not going to be able to take many values that are greater than 1/2, because then the sum won't be greater than 1/2. So intuitively speaking, and I think I've already passed 1 hour, so I'll skip rather fast through the last parts of this algorithm, but just to give you an overview, what it hinges upon is that you have a lot of numbers. You organize them in a table. One side of the table is the ones which are less than 1/2, and the other one is the numbers which are more than 1/2. You can only choose one value from the second column, because if you would choose 2, then the sum would be greater than 1/2. And that wouldn't be a proper state. So it means you can choose at most 1, which is greater than 1/2. And then you take the sum of all the values that are less than 1/2. If that sum happens to be 1, then great, you found your unique solution. Your unique solution has eigenvalues, all of them, each one less than 1/2, and you're done. If it's less than 1, it means that at some point you've chosen wrongly. You should have chosen from the second column. So it means that lambda j is greater than 1/2 for some j, which you now have to find. Okay, so you say, well, 1 is equal to the sum of the lambda i's. This is the sum of all the pi's minus pj, which I've chosen wrongly, plus, so that means that pj has to be equal to s over 2, just from this equation here, for some j. So you look at your values and you say, okay, is there a unique value j for which you find s over 2 inside the first column, because we're in the s less than 1, so s over 2 is less than 1/2. So if there's only one value which is equal to s over 2, then you're done. It means that over there you should have chosen 1 minus s2, and everywhere else you should have chosen pi, and that's the end. If there are 2 values, then it means they are the only values which are non-zero. All the others have to be 0. And if you think about this for a while, you will see why, but I'm not going to labor the point. But basically, you have to distinguish between 2 states. One of them has, let's say, pj and pk are non-zero. Then one of them has the eigenvalue s over 2 for pj and 1 minus s over 2 for pk. And the other one is the other way around. And you have to do that to distinguish between these 2 states. You run the algorithm again, but you slightly permute the orthonormal base is by leaving, for example, just Pj fixed. And then you do exactly the same thing and you determine the jth eigenvalue of rho. Okay. And then you'll be happy to know that this sort of definition and the reconstruction algorithm also applies to other entropies. So you can take Reny entropies, which are the one parameter family of entropies. For every Q, you can define a Reny entropy. Some of them have names, so distinguished Q equals 0, Hartley entropy. Shannon entropy is when Q tends to 1. Chebyshev entropy when Q tends to infinity. And their quantum counterparts are just the classical Reny entropy applied to the eigenvalues of some matrix rho. And these are weakly recursive. There's not a nice recursivity property as in with Shannon entropy, but they're weakly recursive, meaning that you can still define contextual Reny entropy as a function which lands in the global sections of this pre-sheaf. It just means that you'll assign larger values to larger contexts. And then these are sure concave. That's what it was. That's what you needed to get the quantum counterpart arising as minima. It had to be sure concave. So it means that it swaps majorization order. And so the quantum counterparts also rise as minimal among maximal contexts. And if you plot these entropies for distributions of 2 parameters, you get these same sort of shape. So again, you can do the state reconstruction because for every K, you can just choose 2 values and put them in a table like we did before and run the algorithm and nothing being very much. Okay, so the thing to take away is that contextual entropy it's more than just an entropy. It's an information theoretic characterization of quantum states in terms of data that's actually operationally available, because you never have access to the quantum state. You have access to the distributions that you get in various contexts from a set of identically produced quantum states. So it's almost like tomography. You have this distribution, you can retrieve the state. You're locally classical and globally quantum, that's our motto. And one thing to notice is that the properties that we've mentioned so far, namely positivity, additivity, continuity, and whatever we've mentioned, don't fully characterize contextual entropy, or they could for all I know, but we haven't been able to prove it yet. So it would be interesting to find an axiomatic characterization of which order preserving functions are actually contextual entropy maps, because there might be order preserving functions which satisfy all the properties but are not contextual entropy maps, because that would be equivalent to a constructive proof of Gleason's theorem, and it would be pretty cool. So my sort of hope in the future is that maybe I'll be able to use, I'm working with Chris Hoynan at the moment, and I know he has some results which characterize the set of contexts in an axiomatic way. So maybe there's something that can be derived from that in order to get a constructive proof. So that's it. Thank you.
Okay, thank you very much.
More questions?
Yeah, are there any questions or comments or any type of feedback?
I have many.
Oh, go ahead. I've got all evening.
No, well, it turns out that like, well, wait a second. I work on like, well, what I've done is kind of very close to what you have done already. So maybe I've thought about all these things already, but well, the first thing is like concerning reconstruction states.
Wait, what's your name? Because I can't see you. I can only see my screen.
Sorry, could
just so I know who I
my name is Juan Pablo Viñó. So like, I don't know, maybe I will put myself on video here. No, the first thing I wanted to comment is like, okay, you have this result about reconstruction of quantum states. And like my thesis advisor, so the Daniel Benecan, he published a preprint recently, so I put the link here, where he shows that like from so in the classical setting, from the Shannon entropy of something that you could also call like different contexts, or if you want, if you have a system with certain number of states, certain number of components. Okay, so for example, let's say you have several random variables, and then you can measure like the entropy of each of these variables, but then you can also like measure like joint entropies of different subsets of variables. Okay, and then this is some sort of classical counterpart of these contexts. And then he also shows that you can reconstruct the classical state of this joint system from either all this data of joint entropies of smaller systems, or equivalent data that would be like the mutual information of all degrees of this joint system. Okay? But the only difference is like in this classical setting anyway, there is some ambiguity that remains. Okay, it's like you can determine almost completely the state, but anyway there is some ambiguity at the end. So what I find surprising in the result is like you can fully determine the quantum state and without any ambiguity. So I don't know, maybe I will read in detail.
I should say there's a caveat. This doesn't work without ambiguity for 2 by 2. But I thought when I was doing the slides, by the time I got to the last slide, I thought I'm not going to finish in 1 hour and leave the details. But I should say that there's some ambiguity. If it's a 2 by 2 state, you have 2 possibilities and you basically can't distinguish. You can show actually that the 2 possibilities give it identical quantum entropies. And you can,
okay. And you know also what is very interesting, like this ambiguity is not a group. So I don't know. There is this, because also like my advisor, he's interested in sort of Galois theory of this, but like it should be something like, I don't know, a little bit more sophisticated than the usual ideas of ambiguity. But well, that was the first comment. So maybe you can compare what you have done with what he does, and maybe there is some relation. I think maybe your ideas go even beyond this just quantum setting, you know, like somehow maybe something more general that has to do with information. Okay.
Yeah, by all means, I should say, send me an email. This is my email.
Okay, well, anyway, the last link I put is the preprint that I was mentioning, but I will send you an email. And maybe the other comment was about this axiomatic characterization, because I think that if you only use this order preserving property, this property maybe is not rigid enough to characterize an entropy. Yeah? So maybe I think what I've done is like to use actually the recursive property as the algebraic feature that characterizes the entropy. You know, well, general people do this. So Shannon entropy satisfies this recursive property, and it turns out that for Neumann entropy, in a certain sense, satisfies also some sort of similar. Not strictly recursive, but like, yeah, you have to change the language. I will send you an email. But yeah, and then, so connected to that, like, I wanted to say that instead of Reny entropy, you can use this Salis entropy. And that one satisfies a recursive property exactly analogous to the Shannon one. And it is concave in the same way. You know? So I think all the analytical things work in the same way. So maybe there is even a stronger analogy with Shannon, with the Shannon case, if you use the Salis entropy, that is, than if you use the
basically one. Anything that for 2 parameters gives something that's kind of that shape will work. Because the only point was that it gave something that's symmetric around the half, so that you have definitely something that's less and definitely something that's greater than a half. I think that's I think if it's something that's a different type of shape, then maybe it's not going to work so well. But yeah, as long as it's weakly recursive, at least it doesn't even have to be fully recursive and short out. That's enough.
Okay. Well, thanks. I'll send you an email.
So remember
Yes,
also
please.
that if there's more discussions on this, you can also post in the Zulip channel. The questions there and the comments will remain virtually forever. So if you want to start any kind of discussion, that's a good place. Plus, of course, there's going to be breakout rooms at the end of the session for more informal conversation, even about math. So any more questions or comments? There doesn't seem to be any more live questions or comments. So any more offline questions, go in the Zulip channel. And if you want to move to the breakout rooms and stay connected, just stay in the call. If you're on YouTube, please connect to Zoom. And for the rest, let's thank Carmen for a very nice talk and the very nice exposition too.
Yeah,
There are a lot of appreciation comments in the chat, both on YouTube and Zoom.
Yeah, well, thanks for inviting me, Paul. I have to say, I really hope that these online seminars become a regular feature even after life goes back to normal and school start again. That would be the best of both worlds. So let's hope there's someone.
We have that in mind. We are already, like David, Brendan, and I are thinking, are having some ideas on what to do once the pandemic is over to keep the best of both worlds. But yes, I completely agree.